Hello, my name is Eric Dowdy, and I will be doing the presentation today on the attitude, determination, and control of the New Horizons satellite. I'd like to start with a brief introduction of the New Horizons satellite and its mission. The purpose of the mission was to provide deep reconnaissance to Pluto and the Kuiper Belt. The mission also set out to provide a deeper analysis of Pluto's atmosphere, geological structures, and Pluto's surface. For example, NASA set out a list of things it wanted to know about Pluto, like what is its atmosphere made of, and how does it behave? What does the surface of Pluto look like? Are there big geological structures? And how do particles ejected from the Sun interact with Pluto's atmosphere? These are all questions that they wanted answered by the New Horizons satellite. Once its primary mission of Pluto was complete, the satellite would continue deeper into space to observe the Kuiper Belt and objects further. Just so you have a brief understanding of the mission, I will go over the timeline of the New Horizons satellite as well. The beginning of the satellite journey started on January 19, 2006, when it was launched from Cape Canaveral, Florida. Then, over a year later, on February 28, 2007, New Horizons flied by Jupiter for a gravity assist toward Pluto that saved 3 years of flight time. During the long 8-year journey to Pluto, the satellite was put into a hibernation mode. It signaled once a week to ensure that it was still functioning. Along with its once-a-week checkups, the spacecraft also awoke for about 50 days each year in order to conduct an intense set of spacecraft and instrument checks, such as the attitude of the spacecraft, in order to ensure New Horizons was still on target. In the month of December 2014, the spacecraft was finally awoken from its hibernation and planned for its Pluto passing. And finally, on July 14, 2015, the satellite had its closest approach of Pluto. One of the things New Horizons did was take the highest definition photo to date of Pluto, as you can see from the picture in the lower right-hand corner. Now, the satellite will continue its mission further into space to observe the Kuiper Belt and other interesting deep space objects. We will now talk about the attitude determination of New Horizons. Along with its vast number of scientific instruments, the New Horizons satellite also had a good number of sensors used for attitude determination. Attitude determination is performed using star tracking cameras, inertial measurement units, and digital solar sensors. To begin, we will start with the IMU, or Inertial Measurement Unit. The IMU is a self-contained system that measures the linear and angular movements of the spacecraft. The New Horizons satellite actually has 2 IMUs on board, both using ring laser gyros to keep track of any accelerations occurring on any of the 3 axes to monitor body rates. The IMUs are also used as the primary sensor for measuring any delta V in any trajectory correction maneuvers. The IMU data is delivered at a frequency of 100 Hz, or in other words, is delivered at 100 times a second. If the data shows that the spacecraft is out of position, thrusters will be used to reorient the satellite. The New Horizons satellite is also outfitted with 2 star trackers. In the picture on the left, you can clearly see the 2 star trackers. However, only one of the star trackers are ever active at one given time, while the other provides redundancy in case the primary one encounters any problems. The star trackers use charged coupled devices, sensors, to acquire 10 wide-angle images of the star-filled sky every second that are then compared with a catalog of 3,000 known stars to determine the spacecraft attitude relative to these constellations. Last but not least are the sun sensors. New Horizons uses a combination of sun pulse sensors and fine sun sensors to orient itself. The sun pulse sensors provide an electrical pulse whenever the sun passes within their field of view to deliver data on spin rate and help during attitude acquisition, whereas the fine sun sensors locates the sun with high precision in case of an emergency. This will be used in spacecraft safe mode to point the antennas at Earth, since the Earth and Sun vectors will be very similar once the spacecraft is at a great distance of Earth. Overall, the attitude determination system can determine the orientation of the spacecraft with an accuracy of plus or minus 471 microradians in 3-axis pointing mode. When the spacecraft is spinning, the attitude is also sensed at an accuracy of plus or minus 471 microradians, and the spin phase angle is known within plus or minus 5.3 microradians. Now that we know how the spacecraft determines its attitude, we will talk about how it corrects and achieves this attitude. The New Horizon actually only depends on thrusters for propulsion and attitude control. There are no reaction wheels on this spacecraft. The propulsion system uses monopropellant hydrazine thrusters that are fed from a single spherical titanium tank that resides within the central thrust tube of the spacecraft. New Horizon hosts a total of 16 monopropellant thrusters arranged in 5 thruster banks. 4 of these thrusters, making up a single bank, are used as the main propulsion system, each thruster delivering 4.4 newtons of thrust to be able to conduct trajectory correction maneuvers. The other 12 thrusters are arranged in 4 banks of 3 thrusters, each providing 0.8 newtons of thrust. All the thrusters operate on the same principle: the catalytic decomposition of hydrazine over a heated metal catalyst bed to generate combustion gases that are expelled at pressure to generate thrust. For the most part, the thrusters are operated in pulse mode with a pulse length of 5 milliseconds for attitude control. Overall, the satellite was filled with 77 kilograms of propellant and pressurant, 60 kilograms of which was determined was needed for the primary mission with some room for unforeseen maneuvers, and 17 kilograms of surplus propellant in case. Continuing with attitude control, it is interesting to note that the New Horizon satellite has 3 principal attitude modes: 3-axis stabilized, active spin, and passive spin. To begin with the 3-axis mode, the spacecraft can be pointed in a particular direction or be rotated along a particular axis, permitting the scanning and starting instruments to operate during the science phases of the mission. There are 2 modes, the 3-axis normal mode and the 3-axis encounter mode. The 3-axis normal state is normally used during instrument activities including commissioning, Jupiter science, and Pluto approach. 3-axis encounter mode is switched to active during the closest approach to Pluto. It is identical to the 3-axis normal mode in the attitude control mode, but reconfigures the guidance and control system of the spacecraft to prevent a spacecraft safe mode in case of problems with the vehicle to guarantee continued data acquisition during the most critical phase of the science observations. The active spin normal mode is used when the attitude maneuver is needed during a spinning phase of the mission. It is used to maintain the spin rate of the spacecraft and process the spacecraft to a new orientation. And finally, the simplest mode for the New Horizons spacecraft is the passive mode. This mode is utilized the most during the hibernation period of the spacecraft. In this attitude mode, any attitude control is precluded in order to minimize electric power, fuel consumption, and spacecraft monitoring. Overall, the spacecraft attitude control system can keep the spacecraft body rates to within 24 microradians within the 3-axis modes and 34 microradians during spin stabilization. The New Horizons satellite not only set out what it strived to do, it is also still out there gathering data for us as we speak. We learned about its mission and how its attitude was determined and controlled. That concludes my presentation for the New Horizons satellite. I hope you enjoyed listening.